Hi, I am Sanjay Patel. In this video, I am going to prove Leibniz theorem for differentiation. This theorem gives us a way of computing the nth order derivative of product of two functions. Let us write down the statement. If u is equal to f of x and v is equal to g of x are differentiable functions of variable x whose nth order derivative exists, whose nth order derivatives exist. Okay, then we can find the nth derivative of the product of u and v. That is, I can write like this: u into v, and the subscript n means the nth derivative, or dn of u into v by dx raised to n, and this is given by nc0 into un into v plus nc1 into u1 into nc0 into un minus 1 into v1 plus nc2 into un minus 2 into v2 plus, and so on, plus the second last term n in ncn minus 1 into u1 into vn minus 1 plus the last term is ncn into u into vn, and this is true for every n belongs to n. So this statement also we are going to prove using the principle of mathematical induction. This can also be written in a different way, as you can write this as, instead of using u and v, I can write fx and gx and another notation. So dn by dx raised to n of fx into gx. Okay, this we can write as nc0 into fnx into gx plus nc1 into fn minus 1x into g1x plus, and so on. That we write on the last term, that is ncn into u, that is fx into gnx for every n belongs to n. Just we have replaced the symbols u and v by the functions fx, gx. Okay, and as it is to be proved using induction, means for every n belongs to n, we are going to use principle of mathematical induction. So let us prove by induction. So first of all, let the statement Pn, let P of n be this: the nth derivative of u and v, u into v, as nc0 un into v plus nc1 un minus 1 into v1 plus nc2 un minus 2 into v2 plus, and so on, plus ncn into u into vn. Okay, and in this PMI, first of all, we verify the result for n equal to 1. So let us take n is equal to 1 first. What is to be proved in this case? for n is equal to 1, we want to show that u into v 1, that is first derivative of u into v. Now we know that the first derivative of u into v means the first order derivative of the product of the two functions u and v as d by dx of u into v, we can write as say du by dx into v plus u as it is and into dv by dx. Okay, this we can rewrite as u into v. It is the first derivative, so we write uv1. This I can write as u1 into v plus u into v1, because u1 means du by dx and v1 means dv by dx. And now in that required notation, I can write here, say 1c0, because 1c0 is 1 and 1c1 in this way, because 1c1 is also 1, because we know that nc0 and ncn are always 1 for every n belongs to n. So I can write anything I want in place of n here. So, and this is the required result for n equal to 1. So the conclusion is the result is true for n is equal to 1, means P1 is true. Now, as per induction, we assume that this statement is true for n is equal to k. So let us write down this statement again for n is equal to k. That means we suppose that pk is true. Suppose p of k is true, and that is, we can write p of k as u into v, k, the kth derivative or kth order derivative of u into v as kc0 uk into v plus kc1 uk minus 1 into v1 plus and so on plus kck into u into vk. This is we are calling as result number 1. Now our aim is to prove the result, the Leibniz formula for k plus 1, means I want to find the k plus 1th order derivative of u into v. In 1 we have kth derivative of u into v. So if we differentiate this one more time, then we'll get the next order derivative, that is k plus 1th derivative of this left hand side. So let us differentiate with respect to x on both the sides. So now differentiate result number 1 with respect to x on both the sides. Okay, so what do we get here? That is derivative of this is this is some function, you can call it say z. We have zk on the left hand side. If you call this as z, then the next derivative of zk is zk plus 1. So I can write directly this is u into v k plus 1. This is equal to, now we have to differentiate all this term by term because there is a plus sign in between. So we'll write it systematically, and so we can simplify by correcting the proper terms. So what I'm doing is I will start with this first one. Say this term. So kc0 as it is a constant, and then I will write the derivative of uk into v by using the product rule of differentiation for two functions. So uk derivative is uk plus 1 and v as it is, because if we differentiate uk, you will get the next derivative, that is uk plus 1, keeping v as it is, then keeping uk as it is, and derivative of v, the first derivative of v is denoted by v1 like this. then plus the next is kc1 into uk minus 1 times v. So we write kc1 as it is, and now using the product rule for uk minus 1 into v1. So the uk minus 1 derivative, that is uk minus 1 derivative is next derivative. So you have to add 1 to this subscript. For example, if you have y3 and if you differentiate one more time, you will get y4. So whatever is the subscript is there, you have to add 1 to it. So here I will add 1 to the subscript k minus 1 and write directly. So it is uk, okay, and v1 function is as it is. So we are keeping v1 as it is and differentiating uk minus 1. So we'll get uk plus, now keeping uk minus 1 as it is and differentiating v1, what we get is v2. Let us write one more step. Now from the symmetry also you can write without looking at the third term, because here it is not written, but if you want I can mention here that the third term is kc2 into uk minus 2 into v2. So how we should write this step? kc2 into derivative of uk minus 2, that is uk minus 1, and v2 as it is, plus uk minus 2 as it is, and derivative of v2 is v3. Okay, or you can understand this way without looking at this, that just add 1 every time to the subscript of u, and here say v is also increasing, v1, v2. Here in this second group the subscript k is decreasing, k minus 1, then it will be k minus 2, v1, v2 and v3, like that. Okay, fine. And this way we continue, and I want to write now the second last term, that is this in this result number 1. This term, that would be say kck minus 1, that is the previous term, will be u1 into vk minus 1. So the derivative of this can be written in this way: kck minus 1 is constant into derivative of u1 into vk minus 1, that is u2 into vk minus 1 as it is, plus u1 as it is, and derivative of vk minus 1 is vk, plus now the last term, the derivative of the last term, that is kck, we can write as this is u and this is v. So again using the product rule, derivative of u is u1 and vk as it is, plus u as it is now, and derivative of vk is vk plus 1. Okay, so now you concentrate on this thing. Let me remove this part. Okay, and what I want to do next is I want to simplify this by correcting the proper terms. What I am going to do here is I will take this first term and the last term separate. So this is equal to kc0 into uk plus 1 into v. So I'm taking the first term kc0 into this, like that. Now if you look at the next term, that is kc0 into uk into v1, and that occurs at two places. This is uk into v1, and here also we have uk into v1. So if you expand and correct these two terms together, what we can write in the next step is this. It is uk into v1 common. So kc0 from the first term, kc0 into uk v1. So kc0 I am writing here, and kc1 into uk v1. So plus kc1 and then uk into v1. Okay, plus now go for the next term. So the next term is uk minus 1 into v2 here, and we can also see a same type of expression uk minus 1 into v2 over here. This is multiplied with kc1 and this is multiplied with kc2. So taking uk minus 1 into v2 common and simplifying, what we can write here is kc1 plus kc2 into uk minus 1 into v2 plus and so on. Now let us concentrate on these last terms. So what I am going to look here is this term u1 into vk and u1 into vk. This term will go with this previous term over here, but that we are not writing. We are writing just these two and the last term separately. So in u1 into vk, which appears at these two places, the coefficient is kck minus 1 and kck. So what we can write here in place of these terms as plus kck minus 1 plus kck into u1 into vk. And the last term, this term, I am taking separately, which is single term. That will not go with anything else. So kck u into vk plus 1. So the first term and the last term are single. Other terms we can add and write like this. So what we are getting here is the k plus 1th derivative of u into v. You can see here, this is u into v, k plus 1. So we get this thing. Let us simplify this using the combination rules. We have a formula for this kind of addition, and that formula, let us recall, which we already explained in the first lecture, that NCR plus NCR minus 1 is equal to n plus 1 CR. So when this n value is same and there is a difference of 1 only between R values, then what we write is we add 1 to the n value and write the maximum of the two values of R. That is R and R minus 1, the maximum value is R. So we keep like this. For example, again, say 3C2, and if we have 3C1, so this 3 is same and there is a difference of 1 in R values. So the final answer for this, adding 1 to 3 and writing the maximum of 2 and 1, that is 2. So this rule we apply in all these places. So let me remove this first. So what okay, so we can write this as this is equal to this kc0 into uk plus 1 into v. This I am keeping as it is. Now kc0 plus kc1, there is a difference of 1 here in the values of R, and n, the n value is same, that is k. So this will become k plus 1c, the maximum value of R is 1, into uk into v1, plus again here the value of k is same and the difference in value of R is 1. So kc1 plus kc2 will be k plus 1 c2. So k plus 1 c2 into the multiplier is uk minus 1 into v2. So plus and so on, plus for this term kck minus 1 and kck, we can write adding 1 to k value and writing the maximum of k minus 1 k as k. So it is k plus 1 c k into u1 into vk, plus the last term we are writing as it is. So that is kck into u into vk plus 1. Okay. Now we know that kc0 and kck, this kc0 and kck both are 1. This is 1. So I can replace that by any other value which gives me 1 of combination. So I can write it as k plus 1c 0 because I need in that form uk plus 1v plus the remaining terms I am writing as it is. So there is no change here. K plus 1c1 uk into v1 plus k plus 1c2 uk minus 1 into v2 plus and so on, plus this last but one term is k plus 1ck and then u1 into vk plus, now for this last term kck is 1, that I am replacing by k plus 1 ck plus 1 into u into vk plus 1, u into vk plus 1. So the reason for this is because kc0 is equal to 1 and it is same as k plus 1c0, or you can say k plus 1c k plus 1 is also 1, which is same as kck. So we have used these two things in the first and the last term, and this is nothing but your pk plus 1. If you put the value of n is equal to k plus 1 in this formula, you will see that uv k plus 1 is k plus 1 0 uk plus 1 v and so on, and the last one will be u k plus 1 c k plus 1 times u into vk plus 1. Hence p k plus 1 is proved. So the conclusion I can write here is therefore pk plus 1 is true, and that is, I can say, what we have proved. Pk implies pk plus 1 is true. This is proved, and therefore p of n is true for every n belongs to n. Okay, and hence the Leibniz theorem is proved. Okay, so I can say hence the Leibniz theorem is proved. Remember, the Leibniz theorem is useful for finding the derivative of the product of two functions, nth derivative of product of two functions. Okay, but when we actually apply this Leibniz theorem, one has to be so careful for finding or choosing the functions u and v. Let me show you. Means in this formula, u into v n, nth derivative, what should be taken as u and v if you are given two functions? So always choose the function whose nth derivative is known to you as u, that is a simple basic rule, whose formula or which we can write very easily, and choose the function v whose derivative vanishes or it becomes 0, in other words, after a certain stage, so that this term, this expansion you can stop after some number of terms. So that is a simple basic rule. Again, remember, choose u whose nth derivative is known to you as u function, and take v as the function whose derivative becomes 0 after some stage. Okay, that is a simple rule but not a rigid rule. We'll see some examples based on this Leibniz theorem in our next lectures. So with this, we come to an end of this lecture, and from the next lecture we are going to discuss problems of successive differentiation of different types. Thank you.